Hello everyone. We are going to do analysis and optimization of the piston which is used in the automobiles. First, let me do the model by using SolidWorks, and then we can easily import that model into Ansys and we can easily do the analysis. So this is the dimensions of the piston which we selected. So for modeling and analysis, we have taken all the parameters from the piston which is used in the Toyota Fortuner engine. So these are the engine specifications, and these are the piston dimensions, and these are the other parameters.
Go to top line and draw a circle of dimension 92 millimeter. So the dimension has 92 millimeter. So then go back, features, select the sketch and features, extruded base, and extrude it up to 70 millimeters. Up to 70 millimeters we have to extrude. So click OK. Then select this face and then sketch. Select the top plane and then draw a circle. This is to make the grooves of the piston rings. Draw a circle of 86 mm. The groove is actually the depth of 3 mm, so that 92 minus 6 is 86 mm. So go back and then features, extruded cut, and then flip side to cut we have to select, and we have to offset. The offset value will be 6 millimeter, and the cutout value will be 3 millimeter. So then select this side, and then select opposite side. So click OK. So see, the groove has formed. So we have to make 2 more grooves. For that, take a temporary axis and then select the axis, linear pattern. So then select this cutout feature, and the number of patterns will be 3, and the distance will be 6 mm. 6 plus 3, 9 mm. So then click OK. So we can see 3 grooves are formed. So then select bottom face, sketch, and then draw a circle of diameter 84 mm. Diameter of dimensions 80, diameter of 84 mm. So we can see here the radius of 42, so the diameter 84, the inner circle. We have to cut out actually 84 mm, and then go back, select features and cut out. The value will be 65 mm. So click OK. So we have to make this portion. So let me do that. So this another file is opening. I will close that first. I will close this. So select right plane and then sketch, go to sketch and draw that cross section. And then select arc. The tangent arc is not happening. Then select arc, 3-point arc, and then this is 1 point, and this is another point, and this is the third point. Go to dimensions, and the distance between these two lines is 21 millimeter. So we can see here the distance is 21 millimeter. So give 21 millimeter, and this side also the same thing, 21 millimeter. Let me select. (21 mm), and this dimension will be 10 millimeter. So I will make the two lines equal. Two lines not perpendicular, parallel, it is equal. So then smart dimensioning, this radius will be 42, R40 is there, so we have to do R40. We have to give R40, radius 40. Then click OK. Then go back and select the sketch and features. In the extruder cut, select through all both. Click OK. So that cutout is happened. So we have to do the this circle. We have to cut out. We have to extrude cut this. Though let me do. Select front plane and sketch. Draw the circle of diameter 25 mm. Diameter 25 mm. And the distance between the center of the circle and this line will be 21 mm. We can see in the drawing also that distance is 21 mm here. So go back and select sketch and sketch and extruded cut. So by mistake I select wall wizard, not wall wizard. Extruded cut. So through all both, then click OK. So we have to make this extruded portion, so that go to the same plane, front plane, and sketch. Here select the circle and convert entities. So then draw another circle of diameter 35 mm. Diameter would be 35 mm. So then go back, select extrude base in future, select the sketch and futures extruded base, and then up to the next. So here this is not from the center, this is at a distance. The distance is 20 millimeter. Let me give the 20 millimeter. We have to offset it by 20 millimeter. That is the main important thing here. We have to give 20 millimeter. So you can see here, that's it. So click OK, and I have to mirror it into other side. So let's mirror it, mirror, and select the front plane, and then future is we have to select the extruded boss. So click OK. So it done. So you can see, and do the fillet for these 4 lines, this one and this one also. We have to make fillet of the radius 10 mm. Radius 10 mm is actually there, 10 mm. So click OK. Radius is the complete. So select top face and go to insert futures. Here select dome, select this face. The dimension should be 5 mm. So we can see the dome portion. The dome is formed at the top. So this is all about the modeling. All things are done. So we have to save it. Save as. Basically we have to save it in the 2 files, on the IGES or step files. I am saving it as step files to import the file into the Ansys software. Yeah, that's all about some model.
Open Ansys Workbench and click on Static Structural. in analysis system in the project environment, and then click on the engineering data to choose the material. Here the default is structural steel, but the most of the pistons were made up of aluminum alloy, so we are adding aluminum as our material. Alloys. And to give the Young's modulus and Poisson's ratio for this material, choose isotropic elasticity, and here change the Young's modulus to MPa. We know the value of Young's modulus, that is 69 GPa, converted to MPa 69 e power 3, and Poisson's ratio is 0.3. And that's all. Go back to the project schematic, and here add the geometry that we modeled using SolidWorks. To add, click on geometry to add to import geometry. Click in import geometry, browse for your piston, and I saved it as Toyota Fortuner piston, and open it. Finally geometry is added. Right click on the geometry and edit geometry in design modular. Now click on import and click on generate to make visible of the geometry, and that's all. Now again come back to the project schematic and right click on the model and click on edit. Under model there is an option called geometry. In geometry you have to select the you select the material which is chosen in the engineering data. We have to assign the material we choose for our newly added geometry. For that, go to select the geometry you have added in the geometry section, and then go to material section. There is a assignment option. Change it to structural steel to aluminum alloy which you choose it in the engineering data, and then go to mesh and right click on the mesh and generate mesh. Once the meshing is done, right click on static structural and insert fixed support. Fixed support should be added to the portion where it is connected to the connecting rod. Here the end of the piston pins are connected to connecting rod, so I am adding all the inner and outer portions of the piston pin to the fixed support, and then click on the apply, and after that add force. There are different forces acting on the piston while the combustion process is going on. That I calculated all the forces and I have given all the forces in the description. A complete report I have given. You can check there, and I will show you a single force, how to add a single force, and rest all you can easily add. And insert force, I am showing frictional force. The frictional force always acts in the direction opposite to the movement of the piston. Here I am showing you the downward frictional force, which acts when the piston is moving from BDC to TDC. It acts from TDC to BDC. Now you have to select the portion like skirt and 3 grooves of the piston. 1, 2, 3. This is the point. I have given all the points for all the forces. You can check it out and apply it. After applying, you should add the direction of force applying the force. for that, change the vector to components, and y component, I am adding the force in downward direction, so negative 100 Newton. Once it is added, you can see the symbol, the arrow mark pointing downwards. It shows that the force is acting downwards. And rest all forces you can add accordingly. And here I added all the forces. First, the frictional force, which is acting downwards. Point of action is the ring grooves and skirt, and this is the forces acts on the opposite direction of the piston movement. And same for frictional force upward. When the piston is moving downward, it acts on the upward direction. The point of application is same, the ring grooves and skirt. And then weight, this is due to the weight of the piston. This is due to weight. The weight forces of the piston generally acts on the downward direction because of the gravity on the piston itself. It is the constant force, it doesn't vary. And the point of application is the downward edges of the piston, and it is perpendicular to the movement of the piston. And also fixed support, that I already showed you. Gas forces, and gas forces due to combustion, these are acting on the direction, and these are acting on the direction towards the crankshaft, downward direction towards the crankshaft. And the point of application is piston crown. The combustion happen on the upper side when this is compression ignition or spark, due to spark ignition or compression ignition. It applies a pressure on the uh, dome shape of the piston, and it apply the forces in the downward direction. And it is 5800 Newton that I calculated. And next one is normal force. And normal force acts on the direction, in the radial direction, perpendicular to the cylinder. And it acts on the same point as frictional, like ring grooves and skirt of the piston. And inertial force acts on the piston pin, inside portion where the piston pin which is connected to the crankshaft, it is connected. And it is calculated using the formula, and it is 1000 Newton. And it is applied in the radial direction. And the next force is upward. When the inertial force is upward when the moment is downward, and inertial force is downward and the moment is upward. Crankshaft force, this is due to the movement of the crankshaft with respect to the piston pin. And it mainly acts on the piston pin where it is connected to the crankshaft. Downward movement, it is also upward. When the piston is moving downwards, it is downward. When it is moving upward, it is upward, same as the piston movement. Piston ring tension force. This is due to the ring tension, piston ring tensions. It is applied on the that ring ends of the piston, and also it is towards the piston center, and the direction is towards the piston axis, center axis. And viscous force, this is due to the oil which is inside the engine cylinder due to the purpose of lubrication. And this acts on the direction opposite to the piston movement. It always acts on the piston opposite to piston motion. Entire piston surface, it is applied on the whole piston surface, because the oil is inside the cylinder. Piston moves inside the cylinder, so it is applied on the whole piston. And it is also same as frictional force in the opposite direction of piston. And the tangential tangential force is due to the piston's circular motion perpendicular to the radius. It acts on the piston's crown, same as the gas force. And the last one is reaction force. And reaction force which acts on the radial direction perpendicular to the piston axis, and it mainly acts on the skirt of the piston. And these are all the forces we added here. And solution. And after this, click on solution and add equivalent. Right click on solution and insert in stress. You have to add equivalent non-viscous stress, one viscous stress. And here it is. After adding the equivalent stress, click on after adding the click on generate or solve. That is already solved in my system. Here you can observe the different amount of stresses acting on the different point, and you can observe the blue color marks the minimum stress concentration, and also the red is maximum. Where the red is noted, here that is showing maximum. Here there is a lot of stress, and in the blue color marked is less stress area. By performing this stress analysis, we identified the areas with lower stress where our model can be optimized. We are optimizing it using topology optimization. By performing stress analysis, we identified areas with lower stresses where our model can optimize it. We are optimizing it using topology optimization. For that, again come back to project schematic, and there is a option called topology optimization in the analysis settings, and drag topology optimization over the solution set like this. And the another portion is created for topology optimization. Now again go to model, go to setup, edit it, now you can see that the topology optimization is added here. And see, you can see that the optimization system and everything added here. For this, click on analysis settings. The iteration should be 500 and the convergence accuracy should be 0.1%, and optimization region is all bodies, and responsive constant is mass, and percent of return should be 15 or 10 as your wish. And then come to solution. In solution information, right click on solution information, insert topology density tracker. Topology density tracker, only one is required. Topology density tracker, and evaluate for all results. Click on solve. Now you can observe the solution here. You can also observe the amount of material removed. Where the stress is minimum, there the material is removed. You can observe the maximum portion, there is no removal of metal. In minimum portion, it removed material. And also in topology density also you can see the animation of it. And by considering all these topology results, we can redesign our whole piston for this weight reducting this weight and all. Uh, Using the results of topology optimization, we can redesign the geometry and perform a static structural analysis to evaluate the stress distribution in the optimized model. For that, we have to right click on the result of a topology optimization section. On that, there is an option called transfer to design validation system. Click on that. It will convert the obtained result to the new static structural module. And okay, and the same procedure that you followed in the A section, that you have to follow in this C statical structural also. Same, the right click on geometry and update it. Finally the geometry is updated, and then again click on the model, right click on the model to edit it. The same procedure will be followed here. Generate mesh, and all the forces are updated from the last static structural analysis, and click again add, right click on insert and add the stress of equivalent stress, and again solve it. You can observe the concentration is different from that model. For this is optimized, there it is 30, the maximum stress was 30, there it is showing 28, the little stress, the little less in stress. And you can also color of stress element, and after considering all the stress and deformation analysis and incorporate final geometry from the optimized process, we redesigned the model to better suit the engine requirement. The diagram illustrates the final optimized design, and this is the final piston design. And additionally, we calculated the original piston wheel weight and optimizer piston wheels. There obviously a reduction in weight, and this concludes that after optimization, the mass is less, and it also increases the efficiency of the engine. Here you can see the animation. Thank you.